Welcome back. In this video, we're going to be looking at another example problem, learning how to do material balances very methodically for a single unit. So our example problem that we're going to be doing here is taken from a textbook by Himmelblau and Riggs. In this example, the problem statement reads, centrifuges are used to separate small particles from a liquid using centrifugal forces. Yeast cells may be recovered from a broth, which is just a mixture of liquids and cells, with a centrifuge. We want to determine the mass flow rate of cell-free liquid if 1.35 liters per second of the broth is fed to the centrifuge, and this broth contains 510 milligrams of cells per liter, and the product contains 50 mass percent cells. In this case, we are to assume that the feed has a density of 0.997 grams per milliliter. Now, one thing I do want to note here is that we have a period right there, okay, after the 510, and that is simply to indicate that we have three significant figures throughout this problem. So our final answer should also contain three significant figures. Textbooks are very explicit about this. Real life, not so much. So remembering our process, we begin by always looking for the basis, okay? A basis could be something that we create, but if they tell us something about the quantity in the problem statement, then we should use that as the basis. In this particular case, they tell us that there's 1.35 liters per second of broth. And then they further describe what this broth is. Now, that's a quantity, but unfortunately, volume is going to be a challenging basis to use. It's going to be much easier for us if we always learn to use mass or moles for a basis. So no problem. They gave us that. They also tell us the density, 0.997 grams per milliliter. Well, I can easily convert milliliters to liters, and so therefore I can use this basis plus the density to tell me that the basis for my problem is 1,345.95 grams per second. Now remember, in the end I'm going to be saying 3 sig figs, but for all intermediate steps I want to use as many sig figs as I get out of my calculator. So, what's the next step? Well, the next step is to draw the picture. So in this case, I have a centrifuge as my process. I have the broth being fed in, and I'm going to have a product that it will be the yeast cells, and I will have a cell-free liquid. In this particular case, they've given a lot of information, and it's ideal to write all of that given information onto the drawing. In the end, I want to be able to disregard the written problem statement and replace it entirely with the picture. It's much easier to work a problem from a picture that's been well annotated than it is from all those words. The next thing I want to do is build the material balance table. So for each of these, I do this for the stream. So I've named these streams 1, 2, and 3 for simplicity. 1 was the feed. Okay. 2 was the final broth, okay, the yeast plus extra liquid. And this is the cell-free broth. Okay. I'm going to name columns for each of my streams. I'm going to, over here on the left-hand side, list out every component. So I have cells and I have liquid. And then I'm going to put in a total, which is just simply the sum of those other two things. I'm going to indicate what units I wish to use. In this case, I'm working with grams per second. That was how I defined the basis. So the total needs to match the basis. But the cells in the liquid, well, I can choose to have those either in grams per second or grams per gram. In other words, I've chosen mass fractions. Now I do want to, if I'm using mass for my basis, I want to use mass up here, but I can either choose mass flow or mass fractions. So I've chosen, because they tell me that it's 50 mass percent cells, I've chosen to work with a mass fraction. So stream 2 is 50% by mass of cells, which means the rest of it must be liquid, so also 50%. The cell-free broth is going to be all liquid and no cells, so I know that that component is going to be 100% liquid and 0% cells. I do not know what was being fed in, but I know the flow rate of that. I do not know the flow rates of these two products, but I can figure them out. So I'm going to list these as unknowns. Now, normally I would list this as an X with a subscript C1, an X with a subscript L1, an F with a subscript 2, an F with a subscript 3, but my iPad didn't choose to enter those in that way. The next thing that I want to do is look at the degree of freedom table. So the degree of freedom table, this will get a little bit more complicated once we add reactions to our system and once I have multiple processes. But I list my process at the top, and then my categories on the left-hand side will be listing the streams, listing the unknowns, looking for how many material balances I can have, how many sum of X equations, how many process specs I have, and then the degrees of freedom. So if you just write these down, let's now go through and think about what these mean. So for the centrifuge, I have 3 streams. 1 came in, 2 and 3 came out. So I just simply list them, okay? This is simply going to be convenient later when you start getting more complicated diagrams. And then I list the unknowns. So I look at the material balance table and I say, for streams 1, 2, and 3, what unknowns are there? So there's the X for C1 and L1, liquid 1, and there's the flow rate for 2 and the flow rate for 3. Okay, so these are just lists, and then I count how many of them I have. So there are 4 unknowns. Now, material balances. I can write a material balance for each component. I know I also can write one for the overall flow, but the ones that count that are independent is going to be 1 per component. So that's going to be 2. Now there are certain exceptions to this. We'll talk about those when they come up. But for now, typically it's 1 per component. Next is the sum of X's. So I look in each of my columns from the material table. So for each of my streams, if I have an unknown X in that stream, then I list a sum of X. So in this case, column 1, stream 1, and so I only have a sum of X is 1, because that was the only stream that had unknown composition. And then process specs. All right, process specs are going to be, if there's any information over in the given information that I have not yet used as a material balance or sum of X or something else. So what I know is that I have 510 milligrams of cells per liter, okay? And I have 1.35 liters per second, and I have this. The one that I have not used, I used this and this in getting the basis. I used this in getting the compositions for the material balance table. I have not yet used this one. So therefore I have one piece of information I have not yet used. So now then I figure out my degrees of freedom. Degrees of freedom is unknowns minus the sum of all of those. So 4 minus 2 minus 1 is 0. If I have 0, then I'm ready to solve. If I have something that's positive, I need more equations. Okay. If I have a negative degrees of freedom, this problem is going to be overspecified. Okay. If it is overspecified, we go ahead and we solve the system of equations, and we check in all of our extra equations. Sometimes overspecified works out, okay, that we still get the same answer no matter which set of equations we use. Sometimes it isn't. Those are going to be the ones that are tricky. In textbooks, very rarely is a problem truly overspecified. In real life, this is going to happen to us frequently. We will be coming back and addressing this a little bit more later in the chapter. So now then, let's start writing the equations out. We said that I could write two material balances, okay? In this particular case, it's a steady state problem, so input equals output. And so I can write a cell balance, I can write a liquid balance, or I can write a total material balance. Take a moment and make sure that these are the things that you get. But basically, it's the composition times the flow rate for each stream. So composition times flow rate, composition times flow rate, composition times flow rate. And the sums of those are going to be my cell balance. I do similarly for the liquid balance. And for the total, I just write the flow rates in and out. Now, there are three equations here. Any two of them are going to be useful. The other one is extra. We'll be using it in the end to answer our questions, or verifying our answers, excuse me. In this case, choose any two, but looks to me like this one's pretty easy, this one's pretty easy, this one here looks a little more complicated. I'll use this to check. So now begin trying to solve the problem statement. So if I go through and do these, well, my system of equations is not completely complete, okay? I have a little bit more information, and I still have that extra piece here, and I have the sum of x equation. So I have my material balances, the sum of x's equals 1, and I have the extra piece of information. So let's see how we can use those. This one, we'll do it next. It's not the order I wrote them in on the paper, but this just simply says for the stream where I have unknown compositions, the sum of the compositions is 1. So therefore, xc1 plus xl1 equals 1. And I can use that to solve for one or the other. Now, this one, my process spec, okay, the other things stated in the problem statement. I need to use that, and usually that's going to be really the critical piece to solving the problem statement. And there's not like a universal set of rules of how to do this. This one we have to use our logic. So we have 510 milligrams of cells per liter. If I would rather work in like grams per liter, since that seems to be more convenient, I change this over to 0.510 grams per liter. And I have 135 or 1.35 liters per second. So that tells me how many grams per second I will have of cells coming in. So how many cells do I have coming in? Oh, well, I know the flow rate and I know the composition. This product is equal to the number of cells coming in. Therefore, I can solve for the xc1, and it's going to be 5.115 times 10 to the negative fourth grams of cells per gram of total feed. I now know xc1, and using my sum of x equation, I now know xl1. Now then, I just simply need to return to those material balance tables, and I can solve for F2 and F3 simply using very basic algebra at this stage. So go through, play the numbers games. I find that F2 is going to be 1.377 grams per second, not very many cells in there, and F3, the cell-free broth, is 1,345 grams per second. Now, in each case, I've carried ridiculous number of cells sig figs. Now I'm ready to come in and answer the question. So in this particular case, what did they ask us to find? Determine the mass flow rate of cell-free liquid. Okay, so the cell-free liquid was stream 3. That mass flow rate to 3 sig figs is 1340 grams per second. I've answered the question. I've completed the problem. Come back for the next video and we'll look at another example.